Hello students, in this lecture we are going to study kinematics of nuclear reactions. Now in the last lecture we studied the conservation laws, all the conservation laws which are needed for the happening of any nuclear reaction. Okay, so let's study the kinematics of nuclear reaction. Now here for instance we have a projectile mx having mass small mx and which is just projecting on a parent nuclei having mass m. Okay, then we are getting production of a daughter nuclei of having large mass my and a smaller particle is also coming out. Okay, so for this reaction let this collide with this and we are getting the scattering of the daughter nuclei in with a particular direction with respect to the x-axis. Theta is making the angle, this my is making theta angle with respect to the x-axis, and this is making phi angle. Okay, so to find out the kinematics, you know that we need to conserve energy and momentum, the linear momentum. So let's conserve the momentum in x direction and in y direction. Okay, so initially if I conserve the linear momentum in x direction, so in x direction the initial before the collision, there if this is the barrier where here we have a before collision process and this is after collision. Okay, so before collision we don't have any y component, we only have x component of the momentum. Now this was initially at rest, so the momentum of this is 0 obviously. So the only momentum of the system before the collision is this mx vx. Okay, and after a collision, now my is making phi angle with respect to the x-axis, then the momentum of this comes out to be my vy cos phi, right? And the momentum of this comes out to be after collision, the total momentum is, the momentum of this is small my vy, and this is actually capital V. Okay, and this is cos theta. So the total momentum after the collision is my vy cos phi plus my vy and cos theta. So by the conservation of linear momentum we can write the linear momentum equation as that this. Similarly in the y direction, now this is in the x direction, this is the conservation of linear momentum. So y direction, initially the conservation without the linear momentum in the y direction is 0. There is no component, there is a linear momentum in y direction before collision. But after collision, now this is going in the negative y direction, this is going into positive y direction. The component comes out to be something like this. Okay, or we can write this as that, why don't we write the small things, small m, the projectile particle and the outgoing particle as something like this. So my vy cos theta comes to the right hand side and we are left with these two things in the this left hand side. So now we are going to square these two equations and add them together, then we will have the cos square phi and sin square phi as 1. So this comes out to be, if I square this, then this comes out to be m square y v square y cos square phi and the square of this whole. Similarly this the square of this whole. Okay, so if I add these two, then the cos square phi plus sin square phi will be 1 and we are left with my square vy square is equal to, now in this side if I open the square, then this is mx square vx square plus my square vy square cos square theta. okay, minus 2mx 2 my vx vy cos theta plus my vy sin square theta, and my vy sin square theta with respect to this my square vy square cos square theta I will get only this, because cos square theta plus sin square theta is 1. Then this thing now just if I convert this into the kinetic energy, then the daughter nuclei is the kinetic energy of k capital Y is actually half m capital Y v capital Y square. Okay, now what do I have? I have this m square y v square y. So if I square this and divide with a y, then what is this quantity? This quantity is actually equal to 2my ky is actually my square vy square. Okay, so similarly I am writing this as this, this as this, and this as this. Okay, yes. Now similarly I am converting the kinetic energy kx and ky, k smaller, now this is small y. Okay, so don't be confused between this y and this y. This is small y and this is capital Y. Okay, yes. Now since non-relativistic kinetic energy is this, so kinetic energy of y comes out to be here. Now I am sending this mass and this 2 in this side, taking 2 as a common and cutting out, and I will get this thing. That kinetic energy of daughter nuclei is actually equal to this. We know, according to energy conservation, that the threshold and the disintegration energy is actually equal to kinetic energy of the daughter nuclei minus kinetic energy of the parent nuclei. Okay, now in the parent nuclei, or we can say reactant, so the kinetic energy of the reactant is only of the kinetic energy of this projectile. There is no kinetic energy of this. In terms of kinetic energy, in terms of mass, in terms of binding energy, we can write Q. You know the disintegration. Okay, so similarly in terms of Q I can write this equation. Okay, now if I write this equation, now bringing out these things in this direction, left hand side, then I will have Q in the left hand side with respect to these things. Now this is actually Q value. This gives the Q value of the reaction in these terms without involving the kinetic energy of the recoil nucleus and the mass of the target nucleus. Now if we don't know the kinetic energy of recoil nucleus and mass of the target nucleus, still we can get the Q value by knowing only the energy of the projectile, kinetic energy of the projectile, by knowing the kinetic energy kinetic energy of outgoing particle, by knowing the mass of the outgoing particle in the projectile, and by knowing the mass of the daughter nuclei only, we can get this Q value. Okay, then the next thing is, if I do conserve for this process, this is the process we are using, x plus x, we are bombarding x to the parent nuclei, and we are getting a daughter nuclei with the outgoing particle. So if I write the total energy of this x, then the total energy of this in the relativistic case, now this is actually the rest mass energy of this plus the kinetic energy. Okay, for x, this is the rest mass energy of this is mx square plus total kinetic energy of this is ax. Okay, so by writing mx square plus ax, similarly the total energy of this is, because this was at rest, so kinetic energy of this is 0, and mx square is the total energy of this. Similarly of the product ay plus myc square plus ay plus myc square, this is the total energy of the outgoing particle and total energy of the daughter nuclei. So in terms of kinetic energy of the respective particles, the Q value, the quantity Q value, disintegration value, can be written as the kinetic energy of the product particles minus kinetic energy of the reactant particle. Okay, So Q is equal to Ey plus Ey minus Ex, and if I take this Ex into this side and I write that Ey plus E capital Y minus Ex, and here I am left with mx c square plus mx capital X c square minus these two mass systems my c square minus my c square is actually equal to this. Okay, and this is Ky as well. So I can write my Ky in terms of masses as well. So where Q is called the Q value of the nuclear reaction, and if Q is positive, then the reaction is said to be exergic, and if Q is negative, then the reaction is said to be endogenic. Means you require some energy to for the process to happen. Okay. So the minimum kinetic energy required for the incident particle. Now this is the kinetic energy required for the incident particle to initiate the process. Okay, and using these kinetics we can get this energy, kinetic threshold energy, right? And now if I require only this Ex, then I can solve this reaction equation to this. Okay, thanks.